All right. Hey, everyone. Okay, jumping right into it. What we're going to do with today's lesson is we are going to learn about area and estimating with finite sums. So just so you're aware where this is coming from, where it's going, you've, at this point in calculus, you've learned about derivatives. You now recently learned about antiderivatives. And so with antiderivatives, what we're going to get into in the very near future is integration, which is how you find the antiderivative. And what that also is going to tell you is the area under the curve of a function. And so to lead us into that process, we're going to start with this. So we're basically going to go kind of back to geometry and deal with rectangles and use a bunch of little rectangles to find the area under a curve of a function. And then in the future, very near future, we'll use an integral to do that, okay, to find the area under a curve. So let's get right into it. Now, what we want to do here, well, actually, let me say it like this first. We're looking at the area under the graph of a positive function. Okay, so I'll draw you a picture with our example so you see what I'm talking about. And what we're going to end up doing is we're going to end up dividing, so divide an interval. And a lot of times you'll be told the interval, so this will be given to you, divide an interval into what are called subintervals. And the way that we do that is let me add in a letter here. We're going to be told how many subintervals. So let's say we're interested, I think the example I'm going to give you, we're interested in from 0 to 6. That's my interval. When x goes from 0 to x goes to 6. And depending on how many subintervals I want to cut that region into, that's what n represents. So I have from 0 to 6 on my x-axis. Let's say I want 6 subintervals. Let's say I want 20 subintervals. And so that whole subinterval idea, the way you figure this out is the notation, first of all, is delta x. Delta just means change. So this is saying the change in x is going to be b minus a over n. So n is how many subintervals, how many spaces I'm going to cut my region into. It's specifically rectangles. And then the b minus a part, let me say what that is, where x is between a and b. That's for your interval. So for what I've been saying for this example that I'm about to show you guys is this would have been the 0 and that would have been a 6. Okay. Now, so that's our interval. Let me just make that very clear. So this is our interval. And n subintervals. The next thing just to mention before we get into our example is how you find the average value of a function. So average value of a function, and to be very specific, again, it's going to be over some interval of x values. So average value of a function on an interval can be found using this formula. So I'll just say equals the area, which is what we're going to be computing with our rectangles that I'm mentioning, and we're going to divide that by the absolute value of b minus a. So from algebra, absolute value just means distance, if you kind of remember that. So this is saying the distance from a to b, or between b and a. And so another way to say this part is divided by the length of the interval. Okay, so we'll work on this. We'll do an example where we kind of use that one as well. So let's jump right into it. So we're going to be estimating the area under a graph. So let's get rid of just this very top part and write down our example. So we are going to estimate the area under the graph of f of x equals 5x cubed between x equals 0 and x equals 6 using, I'll say it like this, each finite approximation given. Okay, and I'm going to give you those finite approximations. So before I give that to you, let me just make sure you're understanding this whole idea here. We're talking about an area that would otherwise be hard to compute. So from geometry, you guys know area of some nice shapes, like area of a triangle. There's a formula for that. Area of a circle, formula for that. Area of a rectangle or a square. What we're trying to do now and what we can use calculus for and integration in the very, very near future is to find area of shapes that are not so nice. They have curves that we can use a function to describe. So let me write down the rest of this problem and then we'll draw the graph so you can see this curve thing I'm talking about. So the first way we're going to estimate, we'll call this part A, we are going to use the following. We're going to use a lower, so it says lower sum with 4 rectangles of equal width. All right, and we'll walk through this so you understand what I'm talking about when I say lower sum. So the very first thing that I would want to do to visually show this to you, because you don't have to see this to compute it, but for this first example, I want you to see it. Maybe this is your first time learning about this in general. I want you to be able to see it. It'll make more sense. So I'm going to graph this function, at least part of it, from x is 0 to x is 6. Now, you can use a graphing utility to do this. You don't have to do this whole thing by hand, but I'm going to draw this out for us. It's going to help us figure out what's going on. Okay, so I'm only going from x is 0 to x is 6. So what I'm going to do is I'm only going to focus on that part of my coordinate system. So 1, 2, 3, 4, 5, 6. So if I just kind of give you a few points. When x is 0, plug that in. 0 cubed times 5 is 0. Now let's keep this black. Okay. When x is 1, 1 cubed times 5 is 5. And so let me just plot a couple points. Let me write it over here to the side so we get a fairly accurate graph. So x and y, I'm just going to do this for a few points. So 0 gave us 0. 1 is going to give us 5. If I plug in 2, 2 cubed is 8. 8 times 5 is 40. 3 cubed is 27. Okay, I'm going to stop doing this part in my head. Let's use the calculator for these larger numbers. So 3 cubed is 27 times 5. That's 135. Next, let's plug in 4. 4 cubed is 64. Times 5 is 320. 5 cubed times 5 is 625. And last, let's plug in 6. 6 cubed times 5 is 1080. Okay. Now I just want to do that because I want my graph, it's not going to look to scale, but I want to at least have the accurate values. So my highest number on here is actually pretty high. I'm just going to say that's 1080. Okay, and then down here, we kind of grow pretty small at the beginning. This is just like 5. So 1 gave us 5. 2 gave us a little higher at 40. And then we jumped up to 135. And then we went to 320. Then we jumped up to 625. and then got up to 1080. All right, so let's get this curve. All right, again, you don't have to draw this for every time you're doing the problem like this. I'm really doing it on this first one, or on this example, because I need you guys to understand what's happening here. So the visual is going to help. So we're only interested in this part of our function. I'm even going to like drop this down. Okay, that was x is 6. We are only interested from x is 0 to 6. We were told that's our interval. And so we are finding the area. So let's see. Estimate the area under this graph. So what we're interested in, and I'm going to erase this because I need to draw rectangles in a minute, but what we're interested in is this. This whole thing right here. This is what we're calculating. What's that area? Like I mentioned a minute ago, we have area formulas for nice shapes, nice geometric shapes. But what about this shape? It kind of looks like a triangle, but not quite because this curves. So because this curves, I don't have a nice geometric formula to find the area, but that doesn't mean I can't find the area. And so that's what we're going to use our math for today, to find the area of something like this. Okay, so I'm going to erase this because I'm going to end up needing to draw some rectangles. Okay, let's get that orange out of there. And part A says to use a lower sum with 4 rectangles of equal width. So let's start with how to separate or like slice or cut up this region into 4 parts because we're told 4. So that number I mentioned earlier, n, in this case, is the 4. So n is 4. Now, my interval starts at 0. It stops at 6. So to find the width of each of my subintervals, another way to say that is how wide is each rectangle? I'm going to use the formula we wrote down. The change in x is b minus a, which was 6 minus 0, over our subinterval amount, which was 4. So we wrote this down a minute ago. This was b minus a over n. Okay, let's simplify this. 6/4 simplifies to 3/2. Or you can call that 1.5 if you want, or 1.5, however you want to say that. So each of my rectangles, so what I'm doing is I'm going to cut this shape, that region, into 4 equal rectangles, equal width rectangles. They're all going to have a width 1.5. So how I'm going to go about this is I'm going to start from the left and just work my way over 1.5 at a time. So here's 0, there's 1, here's 1.5. So my first rectangle, actually, I'm not going to draw up. I'm going to just make a mark for myself. This is at 1.5. I'll explain why in a minute. It has to do with the lower sums. From there, 1.5 plus another 1.5. So watch what I'm doing. I have to now move over another 1.5 length. So 1.5 plus another 1.5 puts me right here at 3. Okay. Then plus another width, excuse me, I think I said length, but let's call it width. Another width of 1.5, 3 and plus 1.5 will put me right here at 4.5. And then plus another 1.5 from there, 4.5 plus 1.5 puts me right here at 6. And so that's a good way to know that I did this right. I ended up at the end of my interval. So visually, I know my graph, my coordinate system is not exactly to scale, but visually, can you guys see that this pretty much looks like equal width? Like I said, it's not perfect, but if I kind of, I'm not going to measure exactly, but it looks like this is about the same width as this, and this, and this. Okay, so that's what we're doing first, just splitting up our region into 4 parts. If this said 20 parts, I would have a whole lot more marks down here, but we're just going to focus on 4. So that was this part. Now the lower sum part, and for part B, I'm going to show you guys upper sums, so you'll get the difference. The lower sum means on my rectangle, because when I draw a rectangle, I have to hit the curve, my curve, that's like the top of my region, in the lowest part. Okay, I have two choices, either an upper part or a lower part. So watch what I'm going to do. I'm going to actually start from the right side so you can understand this. Here, my rectangle right here is going to have this width. And if I draw this up all the way, I'll draw it all the way and then I'll erase because I want you to see the lower sum. So my rectangle will go technically like that. However, the question said to use the lower sum. So notice the 2 points of contact. I touch my curve up here and down here. And so I have to pick, because of this word right here, I touch my curve in 2 points. This one's higher, this one's lower. I pick this one. And so I draw my rectangle like that. And so I'm going to erase the rest of this. Okay, let's do it again. Let's try it for the next one, moving over. So I'll do it in blue again, and then I'll highlight in red the lower part, the lower sum. So my rectangle would go from here to here, 3 to 4.5, and it would go up, and it would go over to the end of this interval. But again, I was told to use the lower sum, the lower end. I touch this curve in 2 points, here and here. If I kind of go up from the edges of my subinterval, I touch the black curve in those 2 points. I have to pick the lower one. So I pick this and I draw my rectangle. So I'm going to erase that. Okay. So let me kind of color coordinate so you can see. Here's one of my rectangles. Let's change the color over here. Here's another rectangle. And I'm splitting up this region into 4 rectangles. I got 2 more. All right, over here, from 1.5 to 3, let's see if we can do it all at once this time and not erase. Between 1.5 and 3, I have to draw a rectangle where I hit my black curve in the lower part. So when I draw from 1.5 to 3, it would touch here and here, if you can see with my hands. It's a little hard to see, but it would touch here and it would touch here. I have to pick the lower one. So I'm going to draw it from here. It touches my curve right there and then go across. And that would be my second, or in this case, our third rectangle. Now, the last one, why I started on the right side is because this one's actually the most confusing one right here. Here's why. Between 0 and 1.5, where do I hit my curve at the lowest end? It's actually right here at 0. So the highest end would hit right here at this blue dot that's already there. But my lower end hits at 0. So why I said this is the most confusing one, it's actually a rectangle with no height. So that one has a height of 0. That's why it looks weird. So I technically have 4 rectangles now. 1 that looks like nothing, 2, 3, and 4. So I have 4 rectangles. And how we do this process is we had this region that I couldn't quite figure out the area of, but now I'm using shapes I know about, which are rectangles, and I'm going to find the area that way. Okay, so here's why we're doing this whole thing, is because the area of a rectangle is just length. Well, it's technically length times width, but I think I'm going to call it height, just to be very clear. I'm going to call it width times height, because I think the height correlates better with the picture if I call that height. You can call it length times width, but I'm going to call it width times height. So we're using math that we do know, geometry technically here, to find the area of a shape we don't know about. I didn't know about the area under that curved function. So each of those 4 rectangles, here's what we're going to do now. We're going to take the individual areas and we're going to add them up. That's why it says sum. That's why the sum was part of the process here, part of the words. So I'll write it in words so that you understand what I'm going to go and do next. Area of rectangle 1 plus area of rectangle 2 plus area of rectangle 3 plus area of rectangle 4 equals our entire area, or an estimate of our entire area. So I'll say total area. Let me put approximately. So approximately total area. And this is under the curve. So officially, this is under the curve of the function. So the process is, the area under this curve is going to be found by estimating it using areas of rectangles, because areas of rectangles are nicely done. So each of these little terms in my sum here, we know one part automatically. We know the width. We know the width of each rectangle was 1.5. So it's 1.5 times something plus 1.5 times something, and so on. Because we already did that calculation earlier on. We said to get 4 equal width rectangles, 4 equal width rectangles, I divide my whole length of my interval from 0 to 6, I divide it by 4, and I get that 1.5 would give me equal width rectangles. So I got my widths down. Now I just need the height of each rectangle. And now this part requires that you do usually some more calculations. So over here on the side, we have some of these numbers, but not quite all of them. The first rectangle, that one's clear from the picture. That one didn't go up at all because we picked the lower side of the rectangle. So that height was actually 0. So that one's done. That one was nice and easy. So that one's done. The second rectangle, we'll look at where the height is at. The height on the second rectangle corresponds to 1.5. So when x is 1.5, I didn't label that on my y-axis. So I have to figure that out. So for this one, I'm going to say f of 1.5. I still have to figure that out. Okay. Actually, I think that might confuse you the way I'm writing it. Let me change this notation up a little bit. So I'm going to leave that blank, but what I'm going to fill in here is f of 1.5. Okay, so let's go back to our function and find out what that y value is. So our function, if you remember, it was 5x cubed. So if I plug in 1.5 into 5x cubed, let's use the calculator for that. 5 times 1.5 quantity cubed. I'm getting 16.875. You can use a decimal, a fraction or a decimal. I think I'm going to just go ahead and use decimals here. So 16.875. And that's going to go in here. Let's give it more space. 16.875. Okay. And then that one is done. Okay, 2 out of 4 done. So what's happening, we'll do it again on the next one. We need a width and a height for each of our 4 rectangles. Once we know them, we multiply to get the area of each rectangle, and then we add up all 4 areas to get the total area. So next base, rectangle 3. Moving over here again. For rectangle 3, look at where the height was at on rectangle 3. The height of rectangle 3 happened for a x value of 3. So the height of rectangle 3 has a x value of 3. So technically there I would need f of 3. But that one was nice. We actually already did that. That was on our side work. So that one we don't have to calculate again. It was 135. So that was 135 from our side work. We had an XY table over there. We had already done this one, so we don't have to do it again. Okay, so that's done. Last of our 4 rectangles. Let's do this one in green. The 4th rectangle here, its height happens right here. And if you go down, that happens when x is 4.5. So this number is going to be what we get from plugging in 4.5. That's how we get that y value, that corresponding y value. Because if I go across, I never found that yet. I didn't find it in my side work. So if I plug in 4.5 into my function, it's going to tell me what the y value was on my black curve here. Okay, so for this last rectangle. So we have 5 times 4.5 cubed, and that number is going to go right into our height spot. So let's plug that in real quick. And 5 times 4.5 quantity cubed is 5. Actually, it's 455.625. Not the nicest number, but that's okay. 455 times 6.25. Okay. So our setup is done. The hardest part is done. The hardest part is, well, there's a couple of things. Dividing your region into subintervals, in our case it was 4, and then usually the majority of the work will happen when it comes to finding the heights, because the heights are usually things you didn't already compute. In our case, we can tell that by looking that the first rectangle had a height of 0. The second rectangle we couldn't tell by looking. We had to plug that x number back into our function. The third rectangle we could tell from our previous work, the y value or the height. And then the last rectangle, we had to do the work again. We had to plug in. So we're ready to add these up and get the estimate of our area under our curve. So let's use a calculator to add. So I have 1.5 times 0. So from here, 1.5 times 0 plus 1.5 times, right here, second rectangle, 16.875. It's 25.3125. The only reason I'm using decimals here is because they terminate. If these decimals kept going, like let's say it was non-repeating and they kept going in my calculator screen, I would opt for the fraction because it would be more accurate, just so you're aware. But because these decimals terminate, it's an accurate answer. Third rectangle, 1.5 times 135 is 202.5. Last rectangle, 1.5 times 455.625. 683.4375. Okay, let's put it all together. So we got our 3 values plus 0, so we don't have to write that. And then we have final answer, just plugging it all back into my calculator. I got 911.25. Okay, let's see if that's what I had got earlier. Yeah, it is. Okay, so this is area, so I'm just going to say units squared. And that's our first one. Okay, we're going to do this again with the upper rectangle sums, but let me see if you're understanding the process really quick. We don't have a nice geometric formula to find the area under the curve, so we used some stuff we do know. We used rectangles. Now, what do you guys think? Is this area, because it was an estimate, is it an overestimate or an underestimate? Visually, hopefully you can tell, it's an underestimate, because look at all the space it didn't even consider. It didn't consider, it left off all this. This was not included, this was not included, not included, not included. So the area under that curve, it's around 911, but that's actually a low estimate. It would be much more. So 2 ways to get a better estimate is to take an upper sum estimate, which we're about to do next, and then maybe take the average of the 2. The other way to do it is to use more rectangles. And that's what this whole thing is about. Over the next couple of lessons, that's what integration is about. We're going to use integration to basically say if we had an infinite number of rectangles, infinity rectangles, if I could fit millions and millions and millions of rectangles in this little space, it's going to give me a super accurate estimation for the area under the curve. So that's some ways to make it more accurate. Integration is the best way, which is what we're going to be doing in the very near future. So we're going to continue this, and I'm going to show you the difference with doing the upper sums. So part B, we're going to use an upper sum with 4 rectangles of equal length. Okay, so I have to change up my picture. I'm going to go ahead and erase and redo this. This is another process. We're redoing it with upper sums. So I've got my curve here. I'm going to try to leave my curve. I'm going to sort of erase everything else just to avoid redrawing it. Okay. The nice thing is we're still doing 4 rectangles, so we don't have to recalculate our width, our subinterval width. But had that number changed, like it didn't say 4, let's say it said 6 or 10 or 2, some other number, we'd have to recalculate how wide each rectangle is. Okay, but we're going to keep those widths. We already did that work. All right, so there's my curve. Looks a little ugly. I erased a whole lot. Let's get that back there. Okay, so again, we're estimating the area under here. Because 4 is the same number of rectangles as the first one, we get to keep these intervals that we already found. But one more time, if it said a different number, we'd have to recalculate how wide each rectangle is. Real quick, what if it said 6 rectangles? That one's an easy one because this interval is length 6. So if it said 6 rectangles, that one would be the fastest because we would just go with 1, with 1, with 1 on every tick mark on our x-axis. That would have been a nice way to split up our interval into subintervals. Okay, so this time the new part is the upper sum. So I'm going to draw my rectangles again, this time from the highest point where it touches your curve. So I'm going to start on the right side again, just because the way this curve is going up, it's just going to be easier for me to start over there. If this curve was going down, I'd probably start on the left. So from 4.5 to 6, if I draw my rectangle, notice what happened. Let me just sort of draw part of it. I would hit my curve, my black curve, here and here. This time, I'm told to use upper rectangles. So out of my 2 choices of where I'm going to hit my black curve on this interval, I have to pick the upper one. So I'm going to draw this rectangle going up. And then complete it all the way down to 4.5. Whoops, let's color that in. And so this red rectangle here is our first one. Let's fill that in. Well, one of our 4. That one's done. Okay, let's repeat the process for the next subinterval. We'll move over. So between 3 and 4.5, if I go up here to the curve, notice where I hit the curve. I hit it here in this interval, in between 3 and 4.5, and here. I would hit in these 2 points. The end point on the left is here, the end point on the right is here. This time again, I'm told to pick the upper part of my rectangle. So I have to pick this one this time, up here. So I have to draw that one as my height. And so this blue rectangle is my next one. Okay, let's go ahead and color that a little bit. And then moving on to the third out of the 4. And so now, from 1.5 to 3, notice you would hit the curve here and here where my fingers are. And so this time the upper one is on the right side. Okay. And I draw across and line that up with the end point, or the end of this width. And that's my rectangle. And the last one here, this time it's not a height of 0 anymore because On the left was the low one, the low height, or in the lower part of my rectangle. On the right is the upper part. So this time, this is the height. So I always look at my interval, and I look at where do I hit the highest and lowest point. On this one, it happens to be the right side. So I happen to hit on the right side as the highest point. Okay, there's my 4 rectangles. So sometimes the curves do different things. This curve, something kind of nice happened. The lower height on part A was always the left side, and the upper height happened to be always the right side of the interval, the subintervals. Sometimes if your curve does something else, let me just show you real quick. You don't have to add this into your work. I just want you to see it. Let's say your curve did something like this, and your intervals were like, maybe, let's say your interval went from here to here, and here to here. Okay, just a side note for us. If I was told to pick the upper part of this one, the upper sum, let me just sort of draw the edges for you to see. That would be 1 rectangle, 1 rectangle, 1 rectangle. In this first spacing, this first rectangle, the upper part, the highest part of this rectangle would occur somewhere in the middle, right there, right toward the middle area, because that's the highest point on the curve. On this second one, so that's 1, on the second rectangle, it looks like it might occur maybe right there. On the third rectangle, this definitely looks like the highest point, so it happened on the right side. So I just want you to be aware that if your curve is not always going up or always going down, the highest or lowest points might not be on the left or right edge. In this case, it's in like the middle. So just, this is sort of this happens often where it's on the left or right, but just so you're aware, it's not always. Okay, we have our setup. We know the process. We're going to do area of each rectangle. The widths are all the same this time as they were last time. Every rectangle has a width 1.5. So I'm going to just go ahead and erase what's going to change. What's changing is the heights. So let's get that part here. Okay, so same process. Each of my 4 rectangles, I need a width and I need a height. All the widths were 1.5, measured from here. The heights are different, so let's get those heights. This height on the lowest rectangle happens at 1.5. So rectangle 1 has a height of 1.5. So right there, I have to compute f of 1.5, which I think we already did in our previous work. The second rectangle, let me just check that off. The second rectangle, the height looks like it happens at 3. So this is f of 3, which we had done earlier, was 135. The third rectangle, the high point, the height of the rectangle happens right here. And if I go down to my x-axis, that was at 4.5. And then on my last rectangle, the height happens all the way up here at 6, when x is 6. And we actually already did that number. So that one was 1,080. So half of our work is already done. We just have to compute the other half. And I believe we already did this. So let's see if I can remember what our numbers were. When f was 1.5, let me go back in my calculator. This height was 16.875. 16.875. And the last one that we needed to compute for 4.5, that one was the 455. 455.625. Sorry, you probably can't read that. Okay, so this was 1.5, and this was 455.625. Okay, all right. Now we're ready for the sum, which is going to give us the area. Remember, this answer, this time we're using upper sums. Just look at the picture. this is going to be an overestimate because our rectangles are actually outside of our region. They're above it. What we really wanted was down here. So all this part, this, and this, and this, and this, that's extra. It's adding extra to our calculation. So our last answer was like a lower estimate. It was about 911. This answer should be higher than 911. So let's compute this real quick. 1.5. Okay, let's see. 1.5 plus 16.875. Actually, I think I already did this, just to save you some time from watching me on my calculator. Yeah, here's what I got using this one. So this was 2,531.25 square units. So way higher. So what we know is that the area under this curve is somewhere between those two numbers. So the area, actual area under the curve is between 911.25 and 2,531.25. And like I said, one thing you could do here is take the average of the two, and maybe that'll give you a fairly accurate estimation. And the other way to do it is to use midpoints. So I do want to show you this same problem one more time, just to show you the different options. So we're going to do this calculation one more time. We already know that the area is in between here and here. This next time we do it, part C, I'm going to use midpoints. So not the lower, not the upper, but the midpoint. All right, so let's try this. I do want to leave that there because I'm going to plug that in. So let's just work down here. So part C, so same idea. So we're going to use, I'll just say part C, use midpoints. Same stuff about the 4 rectangles. We're not changing anything else. I'm just using midpoints. So let's change our picture first. So one more time changing this crazy picture. Okay. So I'm still using 4 rectangles. So my subintervals are still going to go with the 1.5. All right, let's make that look a tiny bit better really quick. And we have our curve and the area under the curve. Okay, there we go. Now the midpoints. Oops, my marker's drying out. 1.5. Okay, I think I got it to work. So the midpoints, this one's going to require just a little bit of algebra side work. Think of midpoint like an average. So it's like halfway in the middle, or it's the average of the two ends. And so let's start with the first one. This one you can probably do in your head maybe. What's halfway between 0 and 1.5? Because the width of this rectangle is 1.5. So halfway between that is the midpoint. And so for us, that one, like I said, you might be able to do that first one in your head. It's 0.75. So 0.75 gives us exactly the middle, and that's the height of our rectangle. And so if I draw my rectangle across this width of 1.5, I take the height at the middle of the rectangle because I was told to use the midpoints. Okay, let's do this again. This one, if you need to, let's use a calculator. Halfway between 1.5 and 3. So the way that you do this, if you, you can do it a couple of ways, but this might be like the most uniform way. You're going to just take the average. So you're going to say, so I'll do it up here, 1.5, which is my left end point of my subinterval, plus the right end point, which is 3, and I'm going to cut that in half. That's how I find the midpoint or the average. So add those up, divide by 2, 2.25. So the middle right here happens at 2.25. Okay, so I draw my rectangle. Let's change the color. We'll go green this time. This rectangle has a height that happens at 2.5. Okay, let's color this in a little bit. Okay, let's do this 2 more times. Halfway between 3 and 4.5. Same process. You add up the endpoints, 3 plus 4.5, and divide by 2. That's 3.75. So 3.75. And that would be the height of our rectangle. And then last one, halfway between 4.5 and 6, add that up, 4.5 plus 6, take half of it, 5.25. 5.25. And so if I go up from there, watch my marker, I'm going to go up from there, and that's where I hit my curve. And then that's the height of my rectangle. So I use that point to get the height of the rectangle, and then I just draw my rectangle after that. Let's go back to green. Okay. And so there's our 4 rectangles. And so what I want to show you on this one, why this is maybe a better choice for accuracy in this case, is because of the over and underestimation that happens. So look at this. This little tiny piece, if you can see where I'm pointing, it's above my curve. But then this little tiny piece is left open below my curve. Moving on to rectangle 2. This little tiny piece is above my curve, but this open part is left open below my curve. So this process, it's calculating a little bit extra above my curve, but it's also not calculating a little bit under my curve. So it's over calculating with this, with all of these right here that are outside of my curve region, but it's not including this part here. So it's not including this. It's skipping this. It's skipping this. It's skipping where I'm scribbling, and it's skipping this. So this is going to be a fairly accurate estimation because it's overestimating, but also underestimating. So it might be fairly close, like a pretty good estimation. So let's do this one real quick. So our widths are all 1.5 again. And on these ones, what we have to end up doing is we have to find the y value for all of them. We never found any of these y values yet. So our first rectangle, the height of the rectangle was when you plug in 0.75. Okay. The second rectangle was from plugging in 2.5. That's the width, or sorry, the height there. If I plug in 2.25, I'm going to get the height of the second rectangle. The third rectangle height happened at 3.75. And then the fourth rectangle height happened at 5.25. Sorry, yeah, 5.25. Okay, so I have to plug each of those into my function. Remember the function was 5x cubed. So for each of the 3 of these, or 4 of these, I'm plugging into 5x cubed to get the y value, or height of each rectangle. So let's do that real quick. 5 times 0.75 cubed. Okay, these numbers are long, so I'll let you guys do this in your calculator. I'll just fill in the first one because it's not a lot of space to fit these long numbers. This one's 2.109375. Okay. And then you would do that again for the rest. Let's put this in here. There we go. So you would do that here, here, and here with our other 3 f of x values, and then we would add this all up. So let's add this all up real quick. So 1.5 times the number we just got, plus 1.5 times if we had plugged in 2.25 into our function. Okay. And remember, our answer, just so we know if we're on track, it should be between these two other answers. Next one, 1.5 times, have we plugged in 3.75? And the last one, I'm plugging in 1.5 times if we plugged in 5.25. All right, I got this whole thing equaled 1,569.375. And I think that's a pretty good estimate because of our other answers. We underestimated, it was about 911. We overestimated, it was about 2531. And so we used the midpoints and we got a over-underestimate average sort of thing happening here, 1569. So this is a fairly accurate area under this curve. All right, so to sum this up, this process becomes way more accurate if you use more rectangles. And that's why this is happening right before you go deep into integration, antiderivatives and integration. It's because the integral, when you take an integral of a function, it's telling you about the area under the curve, and it's actually taking an infinite amount of rectangles. So not just 4, but 20 or millions, like a bunch. So infinity rectangles. So what's next in the next lesson would have to do with Riemann sums, which is when this number of rectangles increases to like infinity, and then we relate that to integration. If the question asks for average value, remember what I mentioned, you take your area and you divide it by the length of the interval. So let's just add that in at the end here. Average value of the function equals we wrote this down earlier, area divided by the length of the interval. So for us, that's going to look like this 69.375 divided by 6, because our interval had length 6. So let's do that number real quick. So 261.5625. The average value, all this is really telling you about is like your average output. So notice on our curve, we had y is 5, y is 40, y is 135, all the way up to y is 1080. So this is like the average of the values that were outputted from that function. Okay, so that's it for this. I know it's a little different, especially with the calculus. It kind of seems like it's a random type thing, but it's a transition from having just learned about antiderivatives and how it's going backwards from knowing a derivative, getting back to the function, and going into what's coming up next, which is using antiderivatives or integration to find the area under the curve. Okay, have a good day, everyone.